All right, guys, this is example 5.1. This one should give you some Gauss's law flashbacks, essentially. So for this problem, we have a long non-magnetic conductor with a circular cross-section of radius b. And then we have a current I flowing through that non-magnetic conductor. So determine the magnetic flux density inside and outside. So we have essentially a cylinder, and we're looking for the B field outside of the cylinder and then inside of the cylinder. So we have a radius of B for the area that the current is flowing through. Okay, so we're going to use equation 510. And I know there's a lot of writing in this. Literally just only follow the gray boxes. These are just for notes for you guys for later. I'm just following these for the sake of time. But all you need to look at is the gray when you're following along with me right now. Okay, so for the left side, starting out, we know that our B field is always in the phi hat direction for a wire, right? So thumb in the direction of the current, so this way. And then our fingers are going to wrap around. So that gives us our B field direction. So we have B phi in the phi hat direction, so rotating around. Whether we're inside or outside, it's going to be rotating in that same direction. And then we have our DL. So our DL element, we're drawing a circle, a differential line, either inside or outside. For the first one, when we're inside, we're drawing a DL element where our radius is going to be smaller than B because we're inside of the conductor. Okay, we're inside of this non-magnetic conductor. Okay, so talking about our DL, talking about our B, so now let's look at the right side. So when we're circling an area that's smaller than the full charged wire, we are only looking at a portion of the current. So we need to find the current density and then look at, based off of that, like how much current is going through a smaller cross-sectional area. So the total cross-sectional area is a radius of B. The smaller cross-sectional area is going to be inside of that. So that's our R1. Okay, so let's look at what that means. Okay, so so first off, we know that current is equal to the integral of J dot ds, where J is current density. J is also equal to 1 over S. Okay, so in this case, our current density is equal to I divided by the total cross-sectional area, so the total radius of B. Okay, so we're finding the current density. And then for our ds for this one, so we're taking our current density, so the density of our total current, right? And then dotted with the ds of the smaller radius that we're looking at. So the cross-sectional area, which is a circle, which is why we see pi r squared. So the cross-sectional area is with that smaller radius. So we want to know the current density through the smaller cross-sectional area is going to give us the I for that's moving through our inside conductor. So we're looking for the B field due to this smaller like constricted current, essentially. Okay, so we kind of talked about all of our pieces. Now let's put them all together here. Okay, so we have B phi in the phi hat, okay, dotted with R1, so our smaller radius, right? Because we're taking our DL to circle a smaller radius inside of the conductor, right? So if this is like B, this is our smaller radius, R1. So looking at B inside of the conductor. Okay, R1 d phi, so this all the way around here. So the DL is like in a circle, if that didn't make sense to you guys before. DL is a full circle all the way around. And then on the left side, we have this mu naught I. And because we're on the inside, right, we don't have all of the current. We're kind of constricting it. So we need to find our current density first. So current density is I over S, right? So this is the current density as a function of all of the current flowing through. And then we need to look at our ds, or our differential surface, the smaller surface, right, based off of the smaller radius that we're looking at. So the B field due to just the circled area, DL, inside of the larger conductor. Okay? So you should be having some Gauss's law flashbacks here. Okay, so now we're going to simplify this side. So we have this phi hat dot phi hat is going to drop out of the left side. We're simplifying this kind of a lot here. So when we integrated ds, we got the smaller cross-sectional surface here, which ends up here. And then this was our current density that we had, right? So then essentially the rest of this is just algebra. On this side, we have our d phi that we had from our dl, and we're integrating from 0 to 2 pi because we have a full circle. Our dl is a full circle circling the inner conductor, right? dl That DL is going all the way around, so the phi is from 0 to 2 pi for a full circle. Okay, I don't know if drawing all these side pictures is helping or just making more clutter to look at, but whatever. Okay, so then we're solving for a b phi, so we're basically just dividing the other side by this, simplifying algebraically, and then we get our answer here for the b field inside of the wire. So that just required some messing around with the proportion of current and the current density, and then also messing around with our radius. Okay, now we're going to look at the B field outside of the wire. So using the same equation, equation 510, we need to change our DL. We're changing our DL because we're circling a larger cross-sectional area. We're circling a cross-sectional area that is actually outside of the wire. So we're plugging in this R2, which is a larger radius for a cross-sectional area for our DL. We still have that same B phi in the phi hat because the B field is rotational, right? Around, I think I'm pointing in the DL the wrong way. It should be in the positive phi hat. Sorry if that arrow is going the wrong way. But our B field is rotational in the phi hat direction, as always. So it's going around the wire. So that's going to be the same whether we're outside or inside. So we see that here. So then we, on the right side, the big difference here is that we don't have a proportion of the current. We have the full current when we're outside here, so we don't have to do any messing around on the right side. We're just taking that total current. Okay. So again, integrating from 0 to 2 pi because we have a full circle for our DL element, that larger circle. Then we have 2 pi times b phi times r2, and then we're basically dividing the other side. So this is our general solution for the B field outside of the wire. In the very beginning, we did a biosavart problem where we looked at B field due to a wire, and you'll notice that the answer for these when we're dealing with length, as length is significantly larger than r, this is actually the same solution as, I think it's equation 5-35 or 5-34. So basically two different ways to find the same thing. I thought you guys might find that interesting, but again, this problem is a little bit more complicated, but if you need to find a B field inside of a wire, the approach is kind of similar to Gauss's law in terms of the math. There's just some conceptual things going on with the current density that are different. So hopefully this helps clarify a little bit. Just a quick note that DL direction was right the first time. I don't know why I corrected that, but anyway, so thumb in the direction of current. So if current is going this way, your thumb is this way. So this would be like I, and then your fingers are wrapping around. So DL is going around that way. So right the first time.